Howdy y'all, it is I, the Diabolic vTutor, and today we're going to be talking about graphing parabolas. So here we are with the graph, but let's just mention parabolas in brief. So when you're graphing parabolas, well first, what is a parabola? We have the parabola is basically a type of polynomial function. It's just going to be the function f of x. Function of type x power degree 2. So the exponent here is going to be a 2 and maybe plus a few other things. At most x power degree 1 and then technically x power degree 0. And if you've gone through the exponents, this should feel kind of familiar. Okay, so when you see parabola, again, it's just a type of, it's also called a quadratic, but the parabola is, I guess, is a more of a visual sense. So when you break down the word para, it's like besides in Greek, so it's besides, and then you have the bola, which is coming from South America, bola meaning ball. So when you're graphing parabolas, you're literally graphing a pair of these a par-a-bolas. Okay, sorry. Anyway, let's start in the most general form. So when we're talking about graphing parabolas, we have something of the form x squared. Let's talk about the most generic case, which is y is equal to x squared. So what you might see the function written as y is equal to x to the power of 2, in which case I would say that's like the old school way of writing it in terms of when you first learn algebra. You learn to call the one side of the equation y and then the other side of the equation involves x, but as you get farther into math, you start seeing more of this something called f of x notation, which I think this one offers a little bit of a clarity and slightly more information at the cost of it just looks kind of funny in comparison to plain old y. But for now, they're just practically interchangeable. But I'm going to leave it as y first. So when you decide to graph this one, understand what the parental function looks like. And when I say parental function, it's basically this one, the most boring looking parabola that you can get. So y is equal to x squared. So when you're graphing this one, you can do the basic strat of just plotting your points. So we have our xy coordinate right here. We have the x values horizontally, and then we have the y values vertically. So when you decide to graph this one using the tabular strat table form, we're just going to fill out the basic information. So this is a function. You have your x value, that's typically referred to as the independent variable, and then you have the y one, which is the dependent variable, because from a certain perspective, whatever number you put in here, 3 for example, it's going to get squared and then you get a resulting 9. So this 9 here from a certain perspective depended on what you put for the x value or the argument. So therefore, if you put in something like 0 and then for x and then you squared it, you get 0 for y. If you put in positive 1 for x, then you get positive 1 for y, because 1 squared, because if you plug in the 1 value for x, so then you square it, 1 times 1 is simply 1, which is the resulting y value. Alright, so again, kind of a mundane process, you're just plugging and chugging. So you take the 2, if the x value is 2, and then you're squaring it, it's just 2 times 2, which results in 4. So the y value would be 4. So let's graph those 3 points. So we have point number 1, point number 2, and then point number 3. So graphing that one, Maybe I should colorize this, right? Let's colorize this. So this is going to be 0, 0. It's located at 0 on the x-axis and then 0 on the y-axis. Nothing too exciting. And then we have second point, 1, 1. So when the x value is 1, then the resulting y value is also 1. Then for the third point, if x's value is equal to 2, so if the x value is 2, then the y value is 4. Ignore this x. So it's up to 1, 2, 3. And again, if the x value input is 2, then the resulting y value is going to be the 2 squared, which is 4. So 1, 2, 3, and then 4. So that's it. Not the worst thing. So if you connect those ones as quote-unquote smoothly as possible, how do you do that? Well, more on that a little later. We're going to connect that as smoothly as possible. So there it is. If I can do this correctly. Okay. And then the arrow goes upwards forever in a pretty steep fashion. It's increasing at an increasing rate. But if you want a smoother looking graph, all you'd have to do is fill out this table with more data points. So you get a higher degree of smoothness for your curve, but we're not going to fuss over too much of the details. So again, these 3 points, 1, 2, 3, we put them here, here, and here, connected them as smoothly as possible. And we see that as the x values get larger, the y values also get larger. I have a feeling that there's a lot of visual clutter. Let me zoom out. Okay. Move that over right here. And then we'll move this away from the axis. There we go. Okay. But we don't have to graph just the positive values. We could also graph the negative values, which means we just need to go in the other direction. So let me move these particular values down. So further populating this particular table, if we plug in -1, ooh, that's a bad color. If we plug in -1 for x, and then -1 gets squared, it becomes +1. So there it is. And then if we plug in -2 into our function as the x value, then the -2 gets squared, which is +4. There's that one. And then finally, if we plug in something like -3 into our x value, -3 squared is +9. All I need to do is plot those points as well. And again, just to reiterate, the more points you have, the smoother your curve will look. So we're looking at this particular point. If x value is -1, then the corresponding y value is +1. That's nice. If you plug in x value is -2, x value 1, 2, -2, and then the resulting y value would be +4, 1, 2, 3, and then 4. That's easy. And then plugging the last one, 1, 2, 3, x value is -3, then the resulting y value is -3 times 9. Right here. And then now we have more points. We can connect the points as smoothly as possible. It's kind of a artsiness at this point. Alright, there you go. Okay. So a few things to make note of. Number one, there is a bottom portion of your graph. It's right here. You notice that your graph doesn't break past this particular point. And then number two, the arrows go up on the left-hand side and then the right-hand side. That just basically means when you're plugging in larger x values into here, and then you square those large values, you're going to get large positive values. So if you plug in a large size negative number, so for example, -30, and if you square that, you're going to get 900, which is a huge number for y, and the trend will continue to happen if you put if you plug in larger and larger sized values into the x, the resulting y value, which dependent on those x that you chose, will become also larger. So that's why we have this arrow going upwards there, and then the arrow going upwards there. You're not going to get some weird turnaround. Not until you get to other polynomial functions. So for now, we're keeping it simple with just the x squared. Alright, so nothing particularly exciting, but just we'll make note of a few other trends. You may also notice, well, maybe not, but let me point out something. So if you look at your particular function, you can notice there's a certain type of quote-unquote movement from the bottom of the function right here. This one has a special name. It's called the vertex. You're going to see this word a few more times. So vertex, that's just basically the lowest point of this particular graph. In this case, it could, in other type of parabolas, it could be the highest point, but it's either the highest point or the lowest point, or the turning point of your graph, of your function. It might be best to think about it as a turning point for your function. But anyway, that's the vertex. It's colloquially, it's either the highest or lowest point. So in this situation, the lowest value is 0. So we have 0, 0 is the vertex, the lowest point of our function, 0, 0. And this is going to be one of the most important things to pay attention to when you're dealing with parabolas, at least from a graphical sense, maybe in some word problem type of situations as well. But vertex 0, 0 for our parental function x squared. And we're just going to observe some of the movements from this vertex. And when I say movement, I mean moving from one point to the next easy to figure out point, which is this one. So starting from a vertex, if you choose an x value that's one space away, notice the y value is exactly one space up. So I like to call that one the one-to-one movement. And then from this vertex, if you move 2 spaces over to get to the new x, so this is x value 2, you notice that the movement is 1, 2, 3, 4. So it's a 2 to 4 movement. And I'm pointing this out because it's pretty useful for graphing if you understand the way your graph moves away from your vertex. If you hark back to linear functions, which is something like this. Let's look at the linear function real quick. So if you have y is equal to x minus 3, for example, you're going to be looking at a function that's like this. The graph will be like this. So it's called a linear function because the movements from one point to another are going to be a constant rate. So for example, if you choose a point right here, in order to travel to a next point, like right there, it is a 1-to-1 movement because it has a slope of 1. If you choose a different point up here, starting from this y-intercept, you notice that the movement is 1, 2, 3, 1, 2, 3. It's a 3-to-3 movement, which, if you simplify it, it's just a 1. And that should make sense because linear functions have a constant rate of change. It's the same type of movement as you go from one point to another point. As you traverse the graph, it's always the same ratio. So again, if you choose here, for example, and you wish to travel to this particular point, then the movement ratio is 1, 2, 3, 4, 5, 6, 7, 8, 9 to the right, and then you have 1, 2, 3, 4, 5, 6, 7, 8, 9 above. That's a 9-to-9 movement, so consistent with the slope of 1, constant rate of change. So those are linear functions. They're very easy to travel around, which is why a lot of math deals extensively with linear functions, or they try to force linear functions into situations because linear functions behave in a very simple, predictable. A very simple fashion, and then you could use that to predict stuff in the real world. All right. But when you're dealing with a parabola, it doesn't have a constant rate of change. So for example, if you look at point 1 to point 2, it has a certain type of one-to-one movement, which I'm emphasizing. But if you look at to the next point over, traveling from your vertex, it's a 2 to 4 movement. So not a constant rate of change. And when you get to calculus, you can explore that in more detail about how these things are changing, but that's not what we're doing. Okay. So I just wish to emphasize the movement. It's a one-to-one movement for your parental function, and then the next 2 points over, 2 spaces over from the vertex, everything stems from the vertex. It's a 2 to 4 movement, and then lastly, if you move 3 points, 1, 2, 3, it's a 9 movement, which should make sense. Because this is a squaring function, it's not a linear situation with exponent 1. Alright. And you notice that the same thing is happening on the other left-hand side of the vertex. So if you move a 1 space to the left, you move 1 space upwards. If you move 2 spaces to the left, you move 4 spaces. So it's the same ratio movement in sequence. So again, 1-to-1 movement, -1 to +1. 2 movement to the right leads to 4 spaces up. 2 spaces to the left leads 4 spaces up. 3 spaces to the left leads to 9 spaces up, because 3 squared is 9. And then 3 squared is 9. It's supposed to be here. Okay, so just wish to point that out. Alright, delete that. So let's get to a different situation. So why do we care about the vertex? Well, if you know where to plant the vertex of your parabola, it becomes very easy to graph a generic parabola. So let me write down something. Y is equal to x minus 2. So the thing to watch out for, at least early on, is you need to understand how this is different from your parental function. The parental function was x squared. And we know how to graph that. Please memorize how to graph this. How do we graph this? Again, you plot it. To graph your parental function, it's just going to be 0, 0 is your lowest point, the vertex, because it's an upwards parabola. And then you count 1 space to the right, 1 space up, 2 spaces to the left, 4 spaces up, 3 spaces to the right, 9 spaces up. And then you connect the dots. As you see, it's very fast. It's faster than plotting points. But plotting points is always going to be a surefire method. But if you memorize it, it's an additional burden of having to memorize junk. But it's not too bad of a memorization, in my opinion, because technically it's not memorization. It's squaring, understanding how squaring works. So if you move 1 space to the left, you move 1 space up from the vertex, 2 spaces from the vertex, 4 spaces up. 3 spaces from the vertex to the left, 9 spaces up. Well, that's how you graph your parental function with great rapidity, right? But we're not trying to graph our parental function. We're trying to graph this new function. Whoa, whoops, if we put squared. There you go, squaring. So it's very similar to our parental function. In fact, it has basically the same template as you can see right here. The only difference is the subtraction of the 2. And what does that mean? Well, the subtraction 2 just means all you have to do is you are essentially reducing all your y values that you got by 2. So let me clarify that. So this one right here, again, if you plug in like a 2, for example, and you square that, that's a 4. And that normally is where you would put your y value. But if you square the 2 here and then you get a 4, you have to drag that 4 downwards by 2 because you're subtracting 2 from the result. So this y value that would have been here for the parental function, it gets dragged down by 2. So it'll be there. Okay, this is in comparison to our parental function. And then of course, if you plug in a 0 for your parental function, your y value would have been 0. But if you plug in 0 here, 0 squared is 0, and then what happens is the 0 gets dragged down by 2 on the y value axis. So this one goes right here. So what does this mean? It means that all our y values get dragged down by 2. So let me trace the parental function. Let me trace this one. Let me emphasize the points. Here's 1 point. Here's another point. Here's another point. Another. And another clean point. Technically they're infinite points, but we're just trying to pick the easiest. I should have done this on a different layer. Okay, well, unfortunately, hold on. Yeah, different layer. Okay, well, let me put a new layer. Problems of layers. Let me do it again. Okay, there we go. Okay. So when we're graphing this particular y is equal to x squared minus 2, it's just your parental function x squared, just minus 2. So everything gets dragged down 2 spaces. So 1 and then 2. So again, pay attention to how everything has fallen, because this minus 2 here dragged down all the points. So this point dragged down by 2, dragged down by 2, by 2, by 2. This point that I did not point out also dragged down by 2. So everything is dragged down by 2 spaces. So that's what this minus 2 does. In the context of the situation, everything just dragged down by 2 spaces. Alright. So, not too bad. Let me take this and set it back to the parental function position. It's going to be right there. Just trying to beautify it just a little bit. Okay. Transfer that to the top layer. And then this is again, the purple is the parental function. We'll be contrasting the majority of our stuff with the parental function. Alright. So that's if we have a y is equal to x squared minus 2. But what if we don't have that? What if we have something else? So suppose we now have y is equal to x in the parenthetical minus 2, and this is going to be squared. So what if we have something like this and you're supposed to graph your function? Well, this is basically a modification of this particular parental function still. But let me rewrite the parental function. So with the parental function, we can write it with the parentheticals as well. So we have y is equal to, in parentheses, x squared. If you think about it, technically there is a plus 0 inside. Well, maybe. And then you could also, as a placeholder, put a 0 right here. And the 0, 0 should feel very familiar. In fact, it's just the vertex. So vertex is located at 0, 0 because, again, we already established that when we were first graphing the parental function. It's just the lowest point of that particular graph, which is located at, again, 0, 0. So for this one, the vertex is at 0, 0. Well, the parental function. Okay, but we're not dealing with the parental function, we're dealing with a modified type of the parental function from a certain point of view. This one. So what exactly are we doing? There is instead of having a 0 plus 0, we have a minus 2. So if you think about it, what does this minus 2 do? It does something differently than what the minus 2 on the outside did. So basically, when you go back to the previous idea, the minus 2 happens after you do stuff to your x value. So after you squared the x value, you're supposed to get your y value, but the y value gets further reduced by 2. But right here, if we try to put in an x value, before it even gets squared, it gets modified by this minus 2. So it gets decreased by 2. So if you try to put a 0 here, and then if you had squared it before, you would have gotten 0. But you're no longer squaring just a 0. That 0 gets shifted by 2. It gets reduced by 2. So now you're no longer squaring 0. You're squaring a negative 2, which ends up being a positive 4. So understand that. This is a modification, okay? You're modifying your input by subtracting a 2. So what does that mean for our function in terms of graphing it? So the short answer is all it does is it takes your graph and it moves it 2 spaces to the right. And that might seem a little weird because if this is a minus, why are we moving to a positive 2? And the short answer is that's how you maintain the 0 that you had before. And here's what I mean. For your parental function, plugging in 0 here results in 0 squared plus 0, which is 0. So 0 results in 0, which is your x-intercept. But if you try to plug in a 0 here, you're not going to get your x-intercept because now it's shifted by minus 2. So when you try to do 0, square it, it has to first get reduced by 2, so which results in negative 2. And if you square that, that's positive 4. Right here, that's not at the 0 anymore. So how does your x-intercept change? It gets changed because now in order to achieve the 0 that qualifies for x-intercept, you now need a different value to plug into your x. It has to be positive 2 because positive 2, make note of the positive 2 minus the 2 gets you 0, and that when you square it gets your x-intercept, which is right here. So that's, we need a positive 2. So let me reiterate that again. So because we have this minus 2, plugging in 0 no longer gives you a 0. What does give you a 0? Well, any value subtracted by itself will get you 0. So what subtracted by 2 gets you 0? It's positive 2. Positive 2 is here. This is negative 2, not there. Alright? So shifting rows. Where are we? Okay, let me delete this real quick. But don't worry, as we go over more problems, then we will gradually what's the word? Internalize more of these rules. But for now, it might sound very clunky. It might sound overwhelming. It might feel like a lot of rules, but it's going to make a lot more sense when you're actually moving these things around. So again, minus 2 means that you're moving to the positive 2 because positive 2 minus 2 is equal to 0. So let me reset this and start changing some of these values. We're going to do some practices. So suppose I gave y is equal to x squared minus 1. So again, what happens with the situation? The minus 1 is subtracting after the fact of getting the squared. So the main function is the squaring function. So once we square that, we get a y value, but all y values get reduced by 1. So visually, on your graph, that means all your y values have been dragged down by 1 space. And that's it. What if it was in the minus 1? What if you have a plus 4? So again, it means your parental function, x squared, everything's still happening the same as before, it just everything gets moved upwards 4 spaces. So you take your function, perks of the digital medium, and then you drag every single point up 4 spaces. So all the y values get plus 1, plus 2, plus 3, and then plus 4. And then that's it. Pretty basic rule. But what if you have the things in the parenthetical? So if we have x minus 3 squared, for example, what happens? Well, our vertex, the lowest point, has shifted from the 0, 0. Because again, if you try to plug in 0, you're not going to get 0, your x-intercept anymore. What's the new value that will get you your x-intercept? It's positive 3. So positive 3 minus 3 gets you 0. So because it's positive 3, you shift your function 3 spaces to the right, not to the left. Again, the minus 3 is reducing your x inputs. So if if your input was positive 3, it gets reduced by 3, which results in 0 right there. Or you could just memorize the rule. If it's in the parenthetical, it's going to be opposite movement. Which, I don't know. I don't particularly like just memorizing rules. I do like to understand why things are happening, but that's why it's happening. So let's change it up a bit. What if it was y plus 3? We ask ourselves, well, what has happened? There is a modification of plus 3 in the parenthetical, so our input x is being increased by 3, which will cause a shift. What kind of shift? Well, our 0 is going to be shifted. Our x-intercept will be shifted to where? We ask ourselves, how do we produce 0 if x is negative 3? Negative 3 plus 3 squared is 0, which results in our new 0. So x-intercept is no longer there as in the parental function. It's shifted to negative 3. 1, 2, 3. Right here. So you take your entire function, or you take your vertex and you drag it over 3 spaces to the left. 1, 2, and then 3. That's it. So that's in a kind of a dissective approach, but what if we have 2 types of movements? What if you have, for example, y is equal to x plus 2 squared, and then you have a minus 5 right here. We now have 2 things that are differing from our parental function. This one has changed to plus 2, and then that has changed to minus 5. But you follow the exact same rules, and then you just do them one after another. Order of operations will not matter in translation, so you can do either one first. So if you wish, you can account for your left-right movement first, and then you can account for your up-down movement second, or vice versa. It doesn't matter. But I think this one you should do first because it makes more sense from a shifting perspective. So if you think about it, where would your new 0 lie if you disregard this? It would lie at negative 2. So we're going to shift our function to 2 spaces to the left, because negative 1, negative 2, plus 2 gives us 0 intercept. And then we can think about this minus 5. So after the shift 2 spaces to the right, all your y values are reduced by 5, so we move this whole function graph 5 spaces down. 1, 2, 3, 4, and then 5. And that's it. That is the graph of your function. It's good to go. Nothing too exciting. We don't have any... I wrote this wrong. I don't know why I did that. Well, it's supposed to be like that. Hopefully you knew what I meant. That's pretty sloppy. Alright, well, let's put this back to the beginning. And now we're going to see the power of the vertex movement. So without tracing our graph, if we totally disregard our parental function graph, because it is kind of annoying just to graph your parental function over and over, so let's get rid of that. So let's say there's no visual guide for you and you're starting from square 1. So your function that you were given to graph is y is equal to x plus 2, let's do a different, plus 4, and then squared minus 7. Suppose this is your graph. All you need to do is understand how to move your vertex. Well, our vertex always starts off at 0, 0 for the parental function, because 0 squared is 0. Not much to memorize. So what are we doing to our entire function? We're moving it 4 spaces to the left because, again, it's -4. -4 plus 4 gives us 0. So we know our function is moving 4 spaces to the left and then 7 spaces down. All the y values reduced by 7. So all you have to do is take your vertex, which again is normally at 0, 0, and then you move it 4 spaces to the left and then 7 spaces downwards. So take this vertex, 1, 2, 3, 4 spaces to the left, and then afterwards 7 spaces down. This is 5, 6, and then 7. But that's just one point, right? I remember how I told you about regular parental function movements. So from this vertex that you've planted right there, let me colorize that. So the vertex is currently at -4, comma, -7. So once you determine where the vertex is moved, all you need to do is count movements. So the next point over is 1 space to the right, 1 space up. It's a 1-to-1 movement because if you square 1, it's +1. It's 2 spaces to the right from your vertex. Then you move 2 squared, which is 1, 2, 3, 4. So right there. 3 spaces to the right. If you square 3, it's +9. So you have to go 1, 2, 3, 4, 5, 6, 7, 8, 9. There it is. Connect as smoothly as possible, and then the same thing is happening on the other side because your parabola function is perfectly symmetrical vertically through the vertex. But you could still count spaces. -1 to +1 space movement. -2 squared is +4 movement. And then -3 movement is +9 movement for the y values. Connect as smoothly as possible. Well, that's it. That's how you graph it. Very simple. You don't need to graph you don't need to plot points. You don't need to actually draw out your parental function. You just need to understand how your vertex of your parabola is shifted. But these are very simple operations at the moment. We only have translations. In other words, it's only plus or minus left, right, or plus or minus up, down. Nothing too fancy. But let's get to slightly fancier stuff. What if you start having negative values on different parts of your function? So let me delete parental function. We don't really need that anymore. Maybe let's keep that. But let me shrink it. So we're still dealing with the parabola. What if you have something like y is equal to 2, and then we have -x squared? So this looks kind of clunky, but remember your parental function just looks like y is equal to x squared. So what does this negative do for our particular function? Again, if you think about it, this is what you would have gotten for your y value if you just plugged in a number. So if you plugged in +3, for example, 3 squared is 9, you would have gotten 9 if you plugged in 3. But what happens with this negative is that afterwards this negative modifies it, and all your values are now opposite of what they would have been. So if you plugged in 3, you would have gotten a 9 after squaring. You now apply a negative value to your result, resulting in -9. So again, if you tried to plug in +2 into your OG function, you would have been gotten +4. But this negative modification makes it opposite land. So all our y values become their negative opposites. So in graphical form, this just means that you have something called a reflection, a vertical reflection. So again, instead of being 1, 1 for your parental function, the 1 gets -1. So instead of being to +4, the +4 becomes -4, so it's down there. So instead of being 3 squared 9, +9, it's instead -9, so it's down there. So this negative results in the vertical flip of your function. But you can also use your counting principle to graph this function. Here's what I mean. You have 0, 0. Your parental function would have been a 1 to positive 1 movement because there's a technically, remember invisible numbers? There's technically an invisible 1. This is not a slope though, but it's similar in idea to what a slope is, right? So now you have a negative 1 in the front. So instead of being a 1 to positive 1 movement, it is a 1 to negative 1 movement. So 1 to negative 1. So instead of being a 2 to positive 4 movement, if you plug in 2 and you square it and you make it negative, it's 2 to negative 4 movement from your vertex. So here and here. Connect the dots. So instead of being negative 1 to positive 1, the positive 1 gets flipped to negative 1. Negative 2 becomes negative 4 after getting squared and made opposite. Same thing with the 9, the negative 3. Negative 3 squared is positive 9, but the negative forces it in opposite land, so negative 9. There's your graph. Alright, so that's if you have negative values in front of the x squares. There is a funny case where you have a negative inside your function. So if you have y is equal to 2, and then you have a negative x here, and it gets squared, well, does this do anything in terms of reflection for your function? So if you put in the positive 1, it now becomes a negative 1. So it ends up here, but if you square negative 1, it's still positive 1. So it's kind of goofy. Negative 1 to positive 1 movement. So if you try to put in a positive number 2, it becomes a negative input. So it ends up being negative 2 squared. The negative is eradicated. You get positive 2. So that's kind of interesting. So if you plug in a negative 3, for example, the negative 3 becomes an opposite of negative 3. So it becomes positive 3. But if you square 3, it ends up being 9. So technically it has the same movements. It's just things have been flipped in a vertical fashion. So there is a vertical reflection that's going on, but for the most people don't care about it since your parabola is symmetrical in the first place. Again, let me emphasize that. Let me clarify that just a little bit. So your parental function, let me graph it real quick. 0, 0, 1 to 1 movement, 2 to 4 movement, and then 3 to positive 9 movement. So I'm going to color this the positive input side. And then if you plug in the negative numbers, negative 1 to positive 1 movement, negative 2 to positive 4, negative 3 to positive 9. That is the left-hand side of your parabola. What happens is if you have a negative inside your parenthetical before you square, is you just flip, you mirror all your inputs. So the purple inputs which would have been positive inputs, now become negative. Wait, I can't do this. How do I? Oh. Okay, well that's a disaster. Well, let me copy paste this. I'm trying to illustrate a point. So here is your, again, the purple means the positive inputs, and then the other color. Why am I having so much difficulty? Okay. So again, the purple side of your graph resulted from the positive inputs, and then the reddish pink one resulted from our negative inputs. So what happens when you have a negative sign, like right here? Well, what ends up happening is this. Originally your purple values, which were the positive inputs, are now technically resulting on the left-hand side, and then your negative inputs, which now that have become the opposite in the parentheses, now get reflected to the positive side. So there's a mirroring along the axis. Right here, just imagine the graph got flipped along this axis. So there is a reflection, but for practical purposes, it's as if there was no reflection at all. So when you have a negative inside the exponent getting squared, you can simplify it to just y is equal to positive x squared. Because the 2, reviewing our distributive property of exponents, we technically have a negative 1 times an x. So if you use distributive property of exponents, the 2 eradicates the negative sign, so it becomes positive 1, and then here you result in x squared. So it's as if the negative didn't do anything at all, but technically it did do something. It just reflected it across the vertical axis. But again, for all intents and purposes, it's as if nothing happened. Alright, so at this point we have 3, or actually 2 types of transformations that will cause a given nicely written parabola to differ from our parental function. So let's practice some of these. So we have y is equal to x minus 1 squared. Let's do an easy one first, minus 3. So again, you figure out the movement of the vertex first. It moves one space. Is it to the right or to the left? Ask yourself, how do I get 0? If x is positive 1, that's the new x-intercept, right here. And then you gotta shift that downwards 3 spaces. All y values get dragged down 3 spaces. So you take that 1, 2, 3. That is where your new vertex ends up. Again, it moved 1 space to the right, because that gets you to your new 0, and then it gets 3 spaces down. That's the location of your new vertex. So it is at positive 1, negative 3. And then, of course, your graph is going to follow typical parental movement. And by that, I mean it's a 1-to-1 movement to the right, 2 spaces to the right, 4 spaces up, 3 spaces to the right, 9 spaces up. Well, this is a 3, and then this is 6. Yes. Connect the dots as smoothly as possible. There you go. And then, of course, perfectly symmetrical. It follows the same movements on the right hand side. 1 to positive 1, 2, negative 2 to positive 4 movement, and then negative 3 movement to positive 9. Negative 3 squared, it's positive 9. So there we go. All you gotta do. But what if you start putting negatives into the situation? So suppose we have y is equal to negative in the parenthetical x plus 3 squared, and then we have a plus 5. Just consider one thing at a time. Personally, I would, no. Let's just do the typical movements. Again, x-coordinate first is my recommendation. You don't have to, but it makes the most sense in my brain. So how does the plus 3 modify? You're moving 3 spaces to which direction? It's to the left. Ask yourself, how do you make 0? It's at negative 3. So 1, negative 2, negative 3. That's how you determine your x movement. What's the y movement? It's everything gets shifted 5 spaces upwards. So from that last point, 1, 2, 3, 4, 5. There we go. Do we follow typical parental movements from the vertex? No, we have a negative value. So instead of being 1 to positive 1 movement, it's 1 times negative 1. So negative 1 movement. So instead of being 2 to positive 4 movement, it's a 2 to negative 4 movement. 1, 2, 3, 4. Here. So again, positive 1 to negative 1 movement, positive 2 to negative 4 movement from the vertex. 3 to negative 9 movement. And connect this as smoothly as possible. There you go. So same movement on the other side. It's negative 1 to negative 1 movement. This again on the negative 1 right there. It's negative 2 to -4 movement, and then lastly -3 to -9 movement right there. And you're done with the graph. Very simple, very fast. If you understand the basic movements, it's very mechanical. There's not much conceptually going on. If you understand the mechanical movements, then it becomes very nice. I'll just do one more before we get to the next situation. So if we have y is equal to 3 minus 2 minus x squared. Now this is kind of wacky looking. In fact, people would write it in this form just to try to bamboozle you. Don't be fooled by it, okay? So this one, if it helps, you can just move things around yourself. So, if you understand the associative property of algebra, you can move addition in any order you wish. You can only move addition. So, this is technically positive 3. So let me emphasize that. This is a 3. It's not. There's no negative sign. So implicitly understood that it's positive 3. And as long as you keep your signs next to your number, and by next to I mean the number has to be to the right of your sign, you can move it in any order you wish. So you could take this plus 3 using the idea of the associative property of algebra. You can move it right here. And the reason I would recommend doing that is because it's more standardized. This is more of a standard vertex form, it's called, but don't worry about the name. The idea is we want to make it easier for us to identify the movements. So there's a negative flip for our graph, there is a plus 3, and then there's this goofy shenanigan right here. But remember, for a parabola, it doesn't matter what your signage is inside because it gets squared, so it's positive anyway. So you ask yourself the important question. How has the x value been influenced? Well, how do you make 0? It's 2 minus 2. Positive 2 will get you 0. So that's how you know the shift without having to rearrange these terms. So the slow way, if you have this one, is to group them together, put the x first, and then factor out the negative sign. So you have negative x minus 2. So if you're using opposite land rules, then this is going to be 2 spaces to the right. So you see how many, make note of how many seconds that took. To contrast with that, if you just ask yourself, how do you get 0? Why do we want 0? Because that's where the new x-intercept would be if you didn't have this. Where would the new x-intercept be? At positive 2, because positive 2 minus 2 is 0. So here. And then we move the vertex 3 spaces in what direction? It's 3 spaces upwards because the y values are increased by 3. So again, 2 spaces to the right because positive 2 subtracted from 2 gets you 0. 3 spaces up. So 1, 2, 3. There's our new vertex located at positive 2, comma, positive 3. But don't forget the negative. That's where that's what we're going to consider when we're doing movements away from our vertex. So how do we move away from our vertex? It's modified by negative. So instead of being 1 to 1, it's a 1 to -1 movement. Instead of being 2 to 4, as with the parental function, because 2 squared is 4, it's now 2 -4. Usually 2 points is enough for me, but some teachers may require more. So 3 spaces, you move 9 spaces down. Right here. Same thing in the other direction. 1 to -1, 2 to -4. Or you could just lazy it and just transfer the point 1 point over. Exploit the fact that this function is perfectly symmetrical about its central axis. So these y values have the same heights. These y values have the same heights because they're the same magnitude of movement. Same heights. Alright, and we are done graphing this nonsense. Easy. But now let's further make things more complicated. So if we have y to 2 x squared. Now things get a little dicier, but I promise it's not too bad. You're just comparing it to the parental function y is equal to x squared. So conceptually, what is happening in this situation? All your old y values that you were going to calculate and graph now get doubled by 2. So from a movement perspective, right? So if you start off at 0, 0 with the vertex, 0, which is the y value, times 2 is still 0. So nothing happens to the vertex in terms of the movement. But when you move away from the vertex for the parental function, it would have been 1 to 1. But now all your end results are multiplied by 2. So instead of being a 1 to 1 with your parental function, right here, it is instead a 1 to 1 times 2. So it's a 1 to 2 movement, like so. You can kind of see where this is going. So if you consider your movement from your vertex by 2 spaces to the right, instead of being 2 spaces to the right, 4 spaces up, it's 2 spaces to the right, 4 spaces up, doubled. So it's 8 spaces up. So right here. And that is typically enough points because now we're off the chart. So connect those as smoothly as possible. And that's how you talk about this particular movement. So instead of being -1 to +1 movement, you multiply that result, the y movement, by 2. So 2 to 1. No, it's 2 to 1 times 2 here. So instead of being a -2 to +4 movement, it's -2 to +4 times 2. So up there. Connect them as smoothly as possible, and there you have it. Your y is equal to 2x squared graph is done. All it does is modifies movement. Keep track of the one space movement away from your vertex. This is usually tells you a big clue how to do it. Let's do some more. So if you have y is equal to 4x squared, well, that's how your movements are influenced. So number 1, our vertex is still at 0, 0. Because there aren't any plus or minuses, there's no plus or minus to the x, there's no plus or minus out here. So we only have this modification that influences how we move from where we plant our vertex. So we plant our vertex at this default 0, 0 because it's unshifted. Don't count your movements, so instead of being 1 to 1, it's 1 to 1 times 4. Instead of being 2 to 4, it's 2 to 4 times 4. So it's off the charts. It's like right here, 16. You connect it as smoothly as possible. Try to head up to 16. So mirror this movement on the other side. So -1 to +1 times 4. So 1 to 4 movement. So again, it's not exactly a slope, but it's a very similar idea to what the slope does. Again, it's the 1 to 1 movement times 4. And then of course the 2 movement would have resulted in +4, but it gets multiplied by +4. So up here. So there you go. So this is referred to as a vertical stretch because your graph looks like, if you imagine doing the medieval torture back in the days, horse and carrot, what was it called? I don't know, those was torture. Oh, it goes beyond torture. It's also execution, where basically some poor person was tied by their hands to over some sort of pivot point, and then the horses would be pulling the ropes. Okay, let me explain that real quick. So there's a poor person. Poor is an unfortunate. There's an unfortunate person. Maybe a criminal, maybe a wrongly accused criminal. But basically they'd be hung like this, and then there'd be like some sort of stand, and then the rope would be attached like this, looped over here, and there'll be horses on this side, and then they have ropes tied on the other end, horses on this other pair of ropes, and the horse will be moving here, and then the horse will be moving there in the opposite direction. So this person essentially gets stretched on this torture slash execution device, and because human ligaments can only take so much stress, the person eventually gets pulled apart. So that's very, very brutal. Back in the days, what are those called? Criminal punishments, and sometimes they were innocent. So pretty messed up. Thank goodness we're no longer in those times. Alright. So again, that's just going to be a vertical stretch. It's when your function, again, just imagine there's a person, but the person's limbs are getting stretched upwards vertically, so vertical stretch. But let's contrast that visually so you could just see real quick. So if we had the parental function, it would have been 1-to-1 movement, and then 2-to-4 movement, and then 3-to-9 movement. So a little more bottomed out. So -1 to +1, -2 to +4, -3 to +9. So again, it's as if you pull these ones farther upwards, so they get stretched vertically. Alright, let's do some more of those ones, considering vertical stretches and vertical squashes as the other side of things. So if you have y is equal to 1/2 x squared, again, nothing happens to your vertex because there's no plus or minus inside with the x, and there's no plus or minus outside. We do have a 1/2 modifier, so that will influence the movement away from the vertex. And you can imagine, hypothesize what's going to happen. So instead of being, so we plant our vertex here. So instead of being a 1 to +1 movement, what do you think this one's going to do to it? So if you said it's going to be a half movement upwards, you are correct. So instead of being 1-to-1, it's a 1-to-half movement upwards, which you might not feel comfortable graphing halves. So that's why we have other movements. So if you do a 2-to-4 movement for your parental, it gets halved. So it's only a 2-to-2 movement from the vertex. So instead of being a 4, I'm skipping the 3 movement, to 16 movement, it's 4 to half of 16. Half of 16 upwards, which is just 8. So 4 to 8. Connect the points as smoothly as possible. There it is. Same thing on the other side. Instead of being a -2 to +4, it's a -2 to +2. Instead of being a -4 to +16, it's a -4 to +8. Connect smoothly as possible. And there you go. That's how you graph it. This is referred to as a vertical squash. I don't think everyone calls it a squash. I like squash. I don't like the fruit squash or vegetable. Depending if you're colloquially describing a squash, right? I think in botany, squash is considered a fruit. I don't remember. It's not. I don't think it's that simple as just having seeds on the inside. I think the first level is people confusing getting tomatoes mixed up with typical vegetables. So they would say, oh, the tomato is a vegetable. That's like the first level. That's like level 0. And then level 1 is like, oh, wait a minute. The tomato has seeds. So therefore, a tomato is a fruit. And that's like level 1. But then when you get to level 3 botany, there's like, it has to be the flesh of the ovaries or something. I don't remember. It's complicated. It's science. It's coming up with a bunch of words to categorize things into boxes, you know? But why am I talking about this? Squashes. Okay, so let's do another one. So if you have y is equal to 1/3 x squared, this is also not bad. Again, no left-right movements because there's no plus or minus associated with the x. There's no up-down movements because there's no plus or minus associated on the outside. So planet the vertex at 0, 0, our movements from the vertex are influenced by this 1/3, so I would just count by 3 spaces to have an easier time graphing things. So if you want to, you can do a 1 to 1/3 movement, but you might, again, not feel comfortable eyeballing that one. So instead, you can do the 3 movement. So from the vertex, if we move 3 spaces to the right, for the parental function, it would have been 9 spaces upwards. But we're getting 1/3 of that because of this modifier. So instead of being a 3 to 9 movement, it's a 3 to 3 movement. Right? And then the next easiest number is a 6 movement. So 1, 2, 3, 4, 5, 6. Normally, if you square a 6, it would be 36. But we have 1/3 of that instead, so it's only positive 12 right here. So, whoops. Oh no. Okay, we're good. So instead of being, again, instead of being a 6 to 36 movement, it's only a 6 to 1/3 of 36, which is 12. Connect the dots. Personally, I would do the 1 to 1/3 movement, so 1 to 1/3. I don't have any qualms with that. So connect, connect, connect. So if you're feeling particularly lazy, 3 spaces. You can exploit the fact that your graph is perfectly symmetrical. So right here. Lazy strats. Cheese the problem if you can. Unless you are doing this on a test that's being graded by your teacher. Fun fact. I taught some students this method before of counting spaces. First you move the vertex and then you count the spaces to graph the parabola, and then my student learned this and it made a lot of sense to them. They used the exact method on the test they took during class, and you know what happened? They got 0 points for those work. So use at your discretion if you're doing a standardized test. This is, I would say, counting spaces is super effective, because let's be real, most of the time for standardized tests, you have very nice axes. But and of course, when you're dealing with much greater numbers, then counting spaces is obviously impractical. At that point, you already have access to calculators. So by then, any method you learn in your schooling days will be rendered obsolete, right? All right. So let us start mixing up these scenarios. So we're going to have y is equal to 2. Let's do a simple one first. So 2 times quantity x minus 1 squared minus 3. So please always take a quick survey. That way you reinforce the idea of transformations in your brain. So how does this deviate from our parental function x squared? Well, we have a minus 1 shift. So that's left-right change. We have a up-down change, and then we have a movement change from your vertex, aka vertical stretch. So we have 3 things that are getting applied to modify our original x squared function. So one thing at a time, please adopt a very dissective approach. How do you make 0? What's the movement, left or right? Well, how do you make 0? If x is positive 1. So here, and then you move it 3 spaces downwards. So down there. And then your movement is 2 spaces. It's a positive 2 modification. So instead of being 1 to 1, it's 1 to 2. Instead of being 2 from your vertex that has been moved to positive 4, it's instead 2 to 4 times 2. So here, if I can count spaces correctly. So again, if you count spaces, 1, 2, 3, 4, 5, 6, 7, 8. Remember, these grids are going by 5s, if that helps. So you connect the dots as smoothly as possible. Yes. Again, from your vertex, if we're doing a left-hand movement and we're not trying to cheese the problem, it's -1 to 2 movement. It is -2 to 4 times 2, which is 8 movement. So -2 to +8 movement here. Connect the dots as smoothly as possible. And then you are done. Everything's done. You have accounted for the shift to the right by 1 space. We've accounted for the shift downwards by 3 spaces down there. And then we have accounted for the vertical stretch amplitude of 2 because it's a 1 to 2 movement, 2 to 8 movement. So everything's good. Easy. Let's do another one. Y is equal to -4 in the parenthetical. We have 2 minus x squared, quantity squared I mean, and then plus 5. But remember, when you're doing these type of problems, they will try to visually bamboozle you. So let me show you what I mean. They're going to do something like this. And that will be the problem you will have been given. So it's just to make things a little more out of order, or maybe they like the leading term to be positive, but technically this is not a leading term because it has a greater degree. So you have to manually change it yourself. Okay. So you're given something like this. It's a lot easier to identify the types of movements if the things are where you first learned them to be, right? So let me start moving a few things around. So y is equal to, we're going to move this to the front. Again, as long as you understand there's a plus in front of the 5, you can take its associated sign and send it to the back. We're going to get -4, 2 minus x squared plus 5. And now this is a more standardized form. There is technically a vertical reflection. I'm sorry, is it vertical or horizontal? I don't remember. I think it's called a horizontal reflection because you get reflected sideways, but for parabolas, it's not a concern. So you ask yourself the question, how do you make 0 to determine the shift? In order to produce 0, the x-intercept before this, is to make it +2. So +2 is where it gets shifted 2 spaces to the right. And then, of course, we have a movement of 5 spaces upwards. All y values get dragged up 5 spaces up to here. Because I knew it because this is a 0, and then this line right here is 5, so it's +5. Right there. So we've accounted for the horizontal shift, and then we've accounted for the vertical shift. Now, finally, we have this 2-pronged attack by this -4 value in front. So again, what happens? Normally you do a 1-to-1 movement for your parental function, but this is a -4. So instead of being 1 to +1, it's 1, wait for it, -4 times 1. So yes, 1 to -4. That's why the 1 movement is the easiest to do, because it literally just matches the number there. So it's a 1 to -4. It's a 2, instead of being +4, it's 2 to -16. How far is that? Well, this is 5, 10, off the chart. Okay. So that's a huge stretch. Something like this. Now using lazy strats, this is a 1 to here, so mirror it across. There you go. Maximum laziness. Again, if your teacher asks you to do a table of values, I feel sorry for you. I'm sorry. I'm sorry for the loss of your time. You're going to have to do it that way, but for efficiency's sake, if you're just doing a standardized test, please count spaces. It's a very strong method. There you go. That's it. If you're a little paranoid, you could always check your answer by plugging in a random point. No, not a random point. You pick a solid point to plug in. So this one right here, that coordinate is 3, 1. So if you want to test your graphical hypothesis, your x value is 3, y value should be 1. So plug it in. So 3, 2 minus 3 is -1. -1 squared is 1. 1 times -4 is -4. -4 plus 5 is +1. So it seems to be supported. So our hypothesis, our graphical hypothesis seems legit. We're good to go. Let's do 2 more examples, and then we're going to go backwards. Again, this is going forwards. If you're starting off with your given function in vertex form. How do you graph? But then eventually you'll be given a graph. How do you get back to your original parental function? I mean, not parental function, your actual function. Let's write f of x function just to be goofy. So we have f of x is equal to positive 1/3. And we have x power 2 minus 5. So not too much happening. We have a downwards movement, and then we have a path movement from the vertex. 1/3. So start off at 0, 0. There's no left-right movement because there's no associated plus or minus with x. Shift downwards by 5 spaces. So our vertex ends up here. How do we move from our vertex? We have a 1/3 multiplication modifier. So instead of being 1 to 1, it's 1 to 1/3. Instead of being 3 to 3 squared, which is 9, it's a 3 to 1/3 of 9 movement, so it's only 3. Alright, so connect that one, connect that one. If you want one more dot, you can do it. Just pick the nearest divisible by 3. So if it's 6, for example, so if you have a 6 movement, it would have been 6 squared is 36. But 1/3 of that is only 12, so you'd be somewhere up here. Please connect as smoothly as possible. It's kind of artsy. There you go. Lazy strat, 3 movements to here, 3 movements, so mirror effect. And from your axis of symmetry, 6 spaces that ways, so you do 6 spaces that ways. There you go, and then you're done with your graph. Test your graphical hypothesis. This is positive 3, negative 2. Let's just verify that real quick. 3 squared is 9, 1/3 of 9 is 3, 3 minus 5 is negative 2. Graphical hypothesis is supported. We have great confidence it is correct. Alright. Well, again, one more problem, and then we'll move on to going backwards if we consider this going forwards. So let's use a different color. Let's do, ooh, that's bad. Okay, that's better. We need a darker color. There we go. Darker and more saturated. Alright, so now let's do g of x. Let's not bias things towards f of x. So we have g of x is equal to 3 times quantity of x minus plus 4 inside the parenthetical squared plus, let's do minus. No, let's do plus. Plus 5, and then we'll put a minus up in front. Yeah, okay. Sounds simple enough. So something like this, again, just keep track of vertex movement. The vertex starts off at 0, 0 by default. Where does it move? It moves into the negative 4 because, how do you make 0? Negative 4 for the x-intercept. 1, 2, 3, 4. 5 spaces upwards, so move up to this nice blue line, and then negative 3 movement modification. So instead of being 1 to 1, it's 1 to negative 3. Instead of being 2 to 4, it's 2 to negative 12. So this is 5 movement, this is 10 movement, this is 2 more, so it's negative 12. Connect them as smoothly as possible. You're done with the right half, left half. Again, there is the idea of a perfect axis of symmetry. Your graph is perfectly reflected about the straight line through the vertex. So if it's a 1 to here, then it's a 1 to there. It's just expediting the process. You don't have to do this. This is a 2 movement, so it's a 2 movement right here. You know, you don't want to double count your spaces if you're striving for efficiency. So there we go, and then we are done with the graph. Let's just label a few things. So the vertex is at negative 4, positive 5. Vertex. And then a point to test. Let's just test this point right here. Never test the vertex because your vertex is uninfluenced by your vertical stretch. So I always pick the one that's easier to plug in, which is just typically 1 space away. on the horizontal. So this point is a good test point. This test point, according to our graphical hypothesis, predicts that we should have, if we plug in a 3 into our function, we should get a resulting 2. Is that correct? So that gives positive 1 squared, 1, and then times negative 3. And then plus 5 is positive 2. So that gives us great confidence this is correct. Perfect. All right, now what? Let us start, as promised. We're going to start going backwards. Ooh, that's bad. Okay, there we go. So what if I gave you a graph of a function, of a parabolic function, and I asked you to determine what is the function, determine the equation of the function, right? And if you notice how I'm constructing the problem, that's already a big clue about how to do this, right? It's all about counting spaces when you're given very nice axes. This only works if you have a very nicely plotted graph. But let me emphasize a few things. This is a point here, that's a point, that's a point, that's a point, and then that's a point. So the most important thing you must first try to identify is the vertex. So again, if it's a nicely designed graph, it's right here. So you notice that the x value is 6, and then the y value is 7. That's the vertex. So we already know the movement from the standard parental position at 0, 0. It's going to be 6 spaces to the right, and then 7 spaces upwards. So we can already write out our skeletal equation for the function in question. So if we call this function g of x, so g of x in terms of our skeletal equation, our work in progress, is going to be in parentheticals squared. The easiest thing to identify is the plus 7 movement upwards. So plus 7. But what nonsense is happening inside there? Well, in order to produce 0, you need to subtract from 6, right? So it has to be minus 6. So again, that one, if you put it here, you have to get a 0 to get the intercept. So 6 minus 6 gives us 0. There it is. Or you can just memorize algorithms. Okay, some teachers teach it like this, okay? So if we call the coordinates of a vertex h comma k, then all you need to do is populate it into your skeletal equation, which by template, you have to memorize this template, will be this. So whatever value here, you plug it directly into here. You have to memorize this. I'm not fond of having to memorize so much useless junk. So if you think about movements, there's less things to memorize, in my opinion. Okay, so again, how do you make 0 from the 6? It's minus 6. So minus 6. This is a 7 movement upwards, plus 7. But there might be a number in front of here, and we know there's a number that's not 1. There's some sort of value right here. We just don't know what it is off the top of our heads. But that's why counting spaces is so strong. So if you consider the 1 movement, it's not up to positive 1, right? It's a 1 to what movement? Negative 2 movement. So it's negative 2, and then you're done. Isn't that absolutely gorgeous? So efficiency is pretty nice. So if you're a little paranoid, you could always check by plugging in the one you did not use to figure out this negative 2. So we use this point, we counted the movement 1 to negative 2 movement to put this down. So you have to use a different point to test. So you can test this one, but let's be a little more robust. I'll test this one. So according to the fact that has been given, this fact is 5, 6, 7, 8. So this point here is supposed to be 8 comma negative 1. So if we test our equational hypothesis, it's supposed to agree with this. Let us see. So if you have positive 8 minus 6, that's 2. 2 squared is 4. 4 times negative 2 is negative 8, and then negative 8 finally shifted by 7 spaces upwards is negative 1. Confirmed. So we have great confidence in our equation hypothesis for g of x, and then we are done. So that's that. Let's do a few more counting ones, maybe 5 examples, 5 random problems, and then we'll call it for today, at least for now. All right. Again, make note of how I designed the problem. So here, here, and then let's do no, let's do a little bit more. No, it's okay, I'll keep it. Yeah. Final decision. We shall call this h of x, and your job is to come up with the equation for h of x. So again, first make note of where the vertex is. It's right here. What is the coordinate? It's 3 spaces there, and then 6 spaces down there. So we have a negative 3 and then negative 6 type of movement. So let's start. So we know it's going to be something squared. It's going to be x. How do we make 0? If we subtract 3, so it must be plus 3. So let me say that again. In order to produce 0 from our vertex, it has to be negative 3 plus what? Plus positive 3. So that's how we generate this part. And then the minus 6 is fairly straightforward. Minus 6, because it's 6 spaces down from the axes. But the question is, what number goes in front? This is an upwards parabola, so we know it's positive movement upwards. So whatever number is in front, it must be positive. Unfortunately, we weren't given a 1-to-1 movement, so we might suspect this is 1-to-1, but the clear point is given here. So it's a 2 to what? So 1, 2, 3, 4, 5, 6, 7, 8 movement upwards. So it's a 2 to 8 movement. The 2 movement for your parenthetical would have been 4, right? But we resulted in an 8. So what's the factorial what's the factor difference? It's a factor of 2, so it must be twice as the distance is twice as much as what we would have expected for the parental function. Again, the parental function we expect for a 2 movement, it would be a 4 movement, but we got twice as much, 8. So the number in front must be an 8, must be a 2. And then that's it. We have basically finished coming up with the equation. If you wish to test, let's test that real quick. So negative 4 comma 2. So if you plug in negative 4, that's negative 1 squared is 1. 1 times 2 is 2. 2 minus 6 is negative 4. So, wait. That's interesting. Did I miscount? 1, 2, 3, 4. Positive 2. Yeah. So if you plug in 4, negative 1 squared is positive 1. 1 times 2. Interesting. Something erroneous has occurred. So this, which is why sometimes it's a good idea to test your answers. Okay. So let's diagnose what has happened. Oh, I just graphed it wrong. The problem itself is wrong. So this thing is not supposed to be here. I miscounted when I designed the problem. It's supposed to be 2 spaces over. So there it is. So this is not going to be negative 4. This is negative 5. Okay, now it should make sense. So the point that we were supposed to get for the written problem is negative 5, positive 2. So now let's check. So that one results in negative 2. Negative 2 squared is 4. 4 times 2 is 8. 8 minus 6 is positive 2, which is consistent. So everything's consistent all the way around. So we have confidence that our graph is correct. All right. So doing some more problems. Let's start with this nasty, not nasty, it's not too bad. Again, make note of how I'm designing the problem. So as a problem maker, I also have to follow the rules. And from the way I'm following the rules, you can keep track of what I'm doing. Make note of, see how I'm keeping track of the spaces. And the rest of it I'm just going to gloss over. Alright, so we have a function f of x, here it is. Represented, graphed on the graph to the right, to the left hand side. What is the equation? Or your function? Equals what? Alright, well, identify the vertex. The vertex is here. It's still located at 0 in terms of the x-coordinate, so there's no left or right movement. So it's going to be standard x squared. That's easy. But the vertex has been moved to this location, so it's going to be 6 spaces upwards. So the y values are +6. And then lastly, we take into account how is your graph behaving after the shift. It's pointing downwards, right? So we have a downward graph. So we know that there's a negative modifier in the front, but the question is, what is it? Unfortunately, here's the first point. If you're not confident IDing what y value that is, do another point. So it's a 2 to 2 movement, right? So it's supposed to be a 2 to -4, accounting for that one. But you're half of what the parental function would have done. Instead of being 4, it's 2 movement, but it's downwards. So it's a half modifier in the front. And we are done with that. So f of x is equal to -half x squared plus 6. Let's test our hypothesis just in case. We use this one, so let us... Oh, this is kind of ambiguous, right? Let's test this one. Because this one, we can't pinpoint exactly where it is. It's like maybe here-ish. So be careful. Always pick the points that are perfectly on the grid, like so. But this is the one we use to figure out that we use to count the spaces. So to not be so redundant, we're going to use this one right here, which is perfectly on the axis, on the grids here. So that point is -2, +4. Let's test. So if you plug in -2 and you square it, that's 4. -half of 4 is -2. -2 plus 6 is +4. It is consistent, so looks legit to me. Final answer. Alright, and of course, to mix things up, you might be given a function, and you might be asked to predict another point. So here is what I mean. You are given a stereotypical dot here, and then let's do that. Again, see how I'm constructing the problem. See how I'm constructing the problem. So here, and then way down there. Okay. So ambiguous. But for sure, for certain, I will give you this point, and I will give you this point, and I will give you that point. So we're going to call this one, a y, generic. You know what? No, I have to name it. I'm going to name it something. So we're going to name this function, let's see, f, g, h, g of x. So there is our function, and then the question, you know, you could kind of see this in standardized tests. They might ask you something like, what is g of negative 4? No, g of negative 1. They are going to ask you this question, perhaps, and then you are given the graph of the function. You're not given the equation of the function, right? You're just given the graph, and they ask you to evaluate g of negative 1. So in other words, you're supposed to have g of x somehow, maybe, and then they're asking you, what if you slam dunk the negative 1 as an input into your function? What will the resulting y value be? So that's what this question is asking for. So once we understand that, if we were given a function, for example, let's say you were given x squared is equal, g of x is equal to x squared minus 5. As an example, if you plugged in negative 1, this will become positive 1 minus 5. The result is negative 4. And that would have been your answer if this is the equation. So g of negative 1 would be negative 4 if this was the function. But is that the function? Is this the function? No, because it's a downwards function. So this is not the function. So what do we plug into? We're not given the equation. Well, here is another side of the situation. So if I had instead asked you, what is g of positive 2, this question is actually very easy as long as you know how to read your graph. So if I'm asking you, what is the value of g of 2? It's just function tracing. So creep along your x-axis until, because this is the x input, so we're not moving in that direction. We're not inputting negative values. We're inputting positive values. So you creep along your x-axis until you hit positive 2. 1, 2, and you ask yourself, am I on the function? Yes, you are visually on the function. You're right here. What's the y value? It is 0. That would be the answer if this had been the question. Another example, if I had asked you what is g of 3, what does that equal to? Well, given this very nice graph, you could just function trace. So starting from 0, 0, our input is not 0. Our input is positive 3. So we creep along our x-axis. 1, 2, 3. We stop there. Are we on our function? No. If you're not on your function, then that's not the answer on your function. 0 is not an answer for 3. So the answer is not 0. Where is our function? It's up here. So we need to count the movements to get to this location. So 1, 2, 3 spaces, so the answer is 3. If they're asking for g of 3, the answer is 3. And that's it. Can we use this strategy to answer the question, what is g of negative 1? Unfortunately, the graph goes off, and that was deliberately by design. So where's your x-axis is 0 here, we want a negative 1 value, so you move 1 space here, and how many spaces? We don't know. We can't count the spaces. We actually can count the spaces, but more on that later. So let's do it the more standardized way. How do we generate our function using counting strats, right? So let's generate the function. Well, first identify the vertex. The easiest thing to find is 3, 3. And we're going to use that to populate our skeletal structure. So g of x is equal to some sort of unknown a value in the front. We don't know what that is. It's times x squared. What goes in here? Well, a positive 3, how do we get that to become 0? Because we want the x-intercept before up-down movements. So 3 minus what gives us 0? 3 minus 3. Pretty nice. Alright. And then, of course, if you identify the vertex, it's 3 spaces off of the x-axis. So it's plus 3. All you need to do is count spaces, right? So from that vertex, how do you go to the nearest point? One space over, one space forwards. So instead of being one space up, it's 3 spaces down. So number 1, it's 3 spaces. Number 2, it's down, so it's a -3 out in front. So let's clean that up. So g of x is equal to -3 parenthetical. There's a bunch of 3's. There it is. Again, if you're feeling particularly paranoid, we can always test points. So let's test this one. This is at 2, 0. So if we plug in 2, -1 squared is +1. +1 times -3 is -3. -3 plus 3 is 0. That is consistent. So our answer is probably good. Don't get too excited though. This is not the answer. In fact, it's a tragedy. A tragedy if you reach this point on a free response and you wrote this, you won't get full credit. The question is asking for g of -1. So let's finish our task. We just have the g of x function. We need to answer the actual question. So what is g of -1? Let's take the -1, slam dunk it in there. So this becomes -1. This becomes -4. Square that. It becomes 16 times -3 gives us -48. Then plus 3 is -45. So final answer equals -45. And then we are done by generating the equation by counting spaces and keeping track of the vertex. And then we plugged in the -1 to answer the question. And we have our final answer. So that's nice. But as I told you, you could actually technically count spaces. Well, at least in your head, you don't have to count physically by literally going over each space. So what do I mean by that? So we're going to still do the main strategy of finding the vertex. So the vertex is still located at 3 spaces to the right, 3 spaces upwards, 3, 3. Okay? Currently, it's located at x value, x location 3. We want to move how many spaces over to get to -1? If you do the math, it's 4 spaces, right? A 4-space movement, right? So that's particularly important to keep track of. So we're doing a +4 movement, or -4 movement to the left. So all we need to do is determine how many spaces will we have to move downwards. So for the parental function, if you're moving 4 spaces to the left, you would have to move 16 spaces upwards, because -4 squared is +16 movement to get to the corresponding point. But we know this is a downwards graph, and we know it has been vertically stretched. How has it been vertically stretched? By 3, -3. So the movement for the parental function, which would have been 16, has now been modified by -3. Still counting spaces, but only using this space. We're not counting all the way down. So -3 times 16 gives us a -48 movement downwards. Where are we moving downwards from? From the y value of 3. So from that y value of 3, you have to move downwards -48 spaces. But I'm lazy to count spaces. So you just add those two. So what is 3 spaces on the y value subtracted by 48? It's -45. And that is consistent with the previous answer, and we did not have to generate the equation. We just literally just used the concept of how to move from your vertex. I hope that's clear. Unfortunately, there's nobody to give feedback. So if you have any questions, I'm sorry, I can't answer them directly in person. But I guess if you leave a comment down below, I can answer your questions. Alright, moving on. Let's do one more problem for posterity, and then that should be it for today, I think. Let's do this one. You know what? Let's do this. 3. Yeah. As I'm writing this down, try to think about how I'm deliberately designing this problem. Here-ish. Three spaces and three spaces. That is that many spaces. Good enough. All right. So let me delete that because I'm just using that to help generate the graph. You cannot see that. I will, however, make things a little clearer. Let's put that there. And here and there. And we shall dub this function standard boring f of x. And your job is to evaluate f of 4. No, f of 10. Do I want, maybe not 10. Let me think about a good number to pick. You know, let's do 10. Let's do 10. Yeah, that's fine. F of 10 is equal to what? Alright, so where to begin? So let's use the shortcut method first, or the counting spaces. Let's not generate the equation for f of x, and instead let's just try to exploit the regular nature of how parabolas move if you're given good points. Okay, remember, all of this is contingent upon having good movements. So we have a vertex here at -2, comma, -3. The nearest point that I've given you is going to be right here. So, you know, you can't trust this because visually that's hard to parse. Where is this located? This one is also hard to parse, but this is clearly on the grid line right here. Or at least it's supposed to be clear. So it's a 3 movement to a 3 upwards movement, right? So +3 and +3. We know that for a 3 movement, for the parental function, it's supposed to be +9. So the +9 has been cut down to +3, so it's been modified by times +1/3. So we know the 1/3 is the modifier in front of the thing that's getting squared, right? That's all you need. And now we count the movement. We're starting from this -2, and we wish to go we wish to travel to an x value of 10. So how many movements is that? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's a movement of 12 spaces, right? And typically, if you have a 12 movement, it's supposed to get squared to 144 movement. That's what the movement upwards for your parental function would be, but this is not the parental function. It's been modified by a 1/3 value, so you have to take 1/3 of that movement, which is what? It's 12 times 4, which is 48. So that is our actual movement from our y value. What is the actual y value? It's -3. So we're moving 48 spaces upwards from our -3, so plus -3. So we're moving up to 45, and that should be our answer, 45. So this is without generating any equations. This is simply the process of counting spaces. But let's check using the long method. And by long method, I mean we're going to generate the function, and then we're going to plug and chug for the function. So it's nice if you can use shortcuts, but only if you're comfortable doing so. Or if you have to, because it's, you know, standardized tests are unfortunately timed. So what do we have here? The vertex is here. It's -2, -3. That is how we generate the skeletal structure. I'm going to count spaces right away. It's going to be 3 movement this is the only nice point that we're given besides this one, so we can't do a 1 to whatever movement. That would be the ideal situation, but we can do a 1 to 3 movement, and again, the 3 movement is the modified movement. The parental function movement is supposed to be 9, so this one came from 9 times 1/3. You can do that mathematically by what it's supposed to be over what it currently is will get you the change, the modifier. So let's start using these values. So we know the number up in front, and when we know the vertex. So drawing up the function, it's going to be, wait, I did this backwards. I'm sorry. The movement is 3, right? Which is less than 9. By how much of a factor? It's 1/3 of what it's supposed to be. So that's the value, not 3. So the value in front is 1/3. Let me color it blue so you can visually see where it has come from. So 1/3, because again, instead of being positive 9, it's 3, which is 1/3 of what the movement is supposed to be for parental, in comparison to the parental. So 1/3 in the front. It's positive because our parabola is moving upwards. Alright, in parentheses we have x what? If we have -2, how do we produce 0 if we plus 2? Because -2 plus 2 gives us 0. That will give us the x-intercept before up-down shift. What is our up-down shift? It's 3 spaces downwards. Well, I'm going to put negative. This is negative. So -3 downwards. And that should be it. Our function is now complete. I should probably change these colors. Just for visual clarity's sake. This is 2. This is -3. This 45 was the hypothesis before, using a different method, just counting spaces and exploiting the number up in front. So it's hopefully 45. Let's see if our equation is good. So let's test using this point. -5, 0. So if we plug in -5, will we produce a 0? So -5 plus 2 is -3. -3 squared is positive 9. 1/3 of 9 is positive 3. 3 minus 3 is 0. So our function hypothesis seems good. Now let's answer the question using our function. So if we plug in positive 10, what happens? Then this becomes 10, and then 10 times 2 is, 10 plus 2 is 12. 12 squared is 144. That should feel familiar because that's how we got this number. And then what's 1/3 of 144? 12 times 12. 12 times 4 is 48. What is 48 minus the 3? It is 45, which is consistent with the first method. So they basically use the same principle. So because of that, we should end up with the right answer, unless some weird happenstance. Alright, so at this point, I think we're good to go. So what have we covered? We basically covered if you are given a parabolic function and it's already written for you in the vertex form. That's basically this form. It is the x plus or minus h. This is some sort of constant. Now let me put it down. So suppose you're given something like this. And this is -5. We should have the tools at our disposal and the language to graph this type of situation. And then of course, vice versa, if you're given the actual function and it's nicely drawn, be very careful. If it's nicely drawn, then you can generate your function given the graphical situation. So where would we put this one for this one? It's one. It's how do you make 0? Positive 1 minus 1 is 0. So it's like here, and then 2 spaces upwards. Up here, it's a negative 5. So it's a pretty big stretch. So again, it'll be at positive 1, positive 2. So something like this. So be comfortable going forwards. Given your equation, generate your graph. If you're given your graph, generate your equation. Again, all of this is contingent upon having very nice numbers or being given the vertex form of your function already. I think later, next time, I'm going to talk about how to generate your vertex form if you're not given vertex form. So for example, if you're given y is equal to 2x squared plus 4x minus 7, this is not in vertex form. How do you graph this? How do you graph this without plugging in points? Because plugging in points is very tedious. We're going to talk about this next time. And then until then, I wish you a good time. Hopefully I'll do some more streaming later on today. So I'll see you next time.